Hello, this is Vincent, and this will be my video for Project 3, Fluid over a Flat Plate. To start this project, you create a fluid flow fluent, and you go into geometry and you change your geometry from 3D to 2D. Then you use new design modeler geometry to create the geometry. So just open that up. We select the the Z axis, and select the XY plane, and we start by sketching our general shape, which is just going to be a rectangle. The next step would be to figure out the units, which would be meter for mine, and then to dimension your system. So the project specified that the length of the flat plate should be 100 centimeters, which is just 1 meter, and uh, didn't specify the height of the system, which is just we just make it something that is far enough away from the boundary region, or the boundary layer, which will just be zero point 0.1. And this will be our dimensions right here. And then we'll lock that in by creating a surface. So surfaces from sketches, select sketch 1 and hit apply. Then we generate. This will be our surface, and that'll be all for our geometry. So we can go back into the workbook, update our geometry, and then start meshing. This will take a little while to open, but should be here. Okay, now we can start meshing. So the first step to start meshing is create a face mesh for the surface, which will just be the surface. We don't need to change anything in here. So we can generate this. Then we can take a look. It's not refined enough just yet. So we're going to start by adding another. We're going to use sizing. And we're going to start by doing the top and bottom of our sketch. Hit apply. And then we're going to change from the type element size to number of divisions. And then this is preference, but from a couple of examples I saw, that 50 divisions worked well. And then we have to change capture curvature to no. We change the behavior from soft to hard. And this will be all for this sizing element. So we can hit generate with this. And we can take a look at the mesh. It's a little more refined, but it still could use some work. And so the next step would be to create another mesh. So sizing. We'll start by sizing on the left side. Hit apply. Change element size to number of divisions. And we change the number of divisions from 1 to 60, which I found works good from previous examples that I saw. Then we can change capture curvature to no. Change behavior from soft to hard. And then we want to have a significant portion of our divisions near the bottom, which will be our plate. So we can change the bias type to this one up here, and we can change our bias factor to 60 as well. And then this should show that our number of divisions is getting more refined near the bottom. So we just click generate. Seems the face mesh is a little weird, but we can continue this. We can then create one more. Insert sizing on this side. Apply. We can change our element size to number of divisions. This again to 60. Capture curvature to no. Soft behavior to hard behavior. A bias to this one right here. I'm going to change our bias factor to 60. And then we can see that this is in the wrong direction. So we're going to have to reverse the bias. Select this bias right here. We can apply. This will swap it so the majority of the divisions are near the bottom of the plate. and the rest of this looks good, and so we can just hit generate. This should have made this plate look nice and complete. Everything is nicely laid out. Number divisions get increased towards the bottom of the plate. So the next step would be to name our sides. So we're going to name this left wall, this left line, inlet. That's where our fluid will be coming in. I'm going to change the right wall to outlet just by hitting N. We'll be setting this bottom one to be called plate or wall. And then we're going to name this top one to sorry, I just wanted to figure out what I named this last time, because that worked well with the automatic settings that it produces. This would be far field. So name this far field. And then I'll name the surface itself airflow. Okay. Looking at the name sections, we should have all 5, which is true. And so now we can go back to the workbench and update our mesh. All right, with this done, we can go ahead and start on our setup. I like to use double precision and a 2 solver processes for mine. Just worked well in the examples that I saw. This usually takes just a little longer than the mesh to open. So let's wait a bit. We'll have a couple of things to change before we can start initializing the project. So let's wait for all the selections to join in, and we'll hopefully see that. Yes, this looks good. As we can see, the divisions get increased towards the bottom. And so now we can check on a lot of the things. So the first thing I'm going to do is we'll change the material of the fluid. We were specified that the fluid would be air, but we were given that the density should be 1.2 instead of 1.225, and that the viscosity should be 1.8 instead of 1.7894. 1.8 e to the negative 0.05. So this should be good. Change/create, and we can close. We can reopen that to confirm that it changed. It did. So we can close that out. So we could also go into models, go to the viscous, and we could change viscous to laminar. Hit OK. I believe this should be it for models. We can close that. Materials is also closed. And so next step would be to check on the boundary conditions. So inlet should be inlet, outlet should be outlet, and then walls should not be far field. We would like to change far field to something else, to symmetry, I believe. So we can select far field and type from wall to symmetry. Just hit apply and then close. This should have made another symmetry for far field. Now we can start changing our inlet settings. So from the project description, we know that the free stream velocity should be 2 meters per second. We just hit apply and then close. We can confirm that again by just opening it again. It did indeed change. We just close that now. And then let me just check my my guidelines real quick. Just will take a quick second. All right, now we can start changing our solution settings. I'm going to change this to simple, and then change that to simple, and then I'm going to change I'm going to change, I'll leave the controls all good, and then initialization, I have some things to change in here from hybrid to standard, and then I want to compute from the plate, I believe, or from the inlet. It was indeed from the inlet, and then we can change this because y velocity should be 0. We should only have this. So it should be inlet relative to the cell zone standard initialization, and you can just hit initialize. All right, this should have worked. Do that one more time to just make sure it worked. All right. I believe that should have worked. Now we go to run calculations. Number of iterations, I saw that 10,000 worked just fine. Actually, I wanted to do one more thing in reference values. No, not yet reference values, not just yet. It was residual, is what I was looking for. I wanted to increase the precision by just a couple of zeros. And then we can run the calculations. So 10,000, 1, and then just calculate. So this will run. It should converge in just a few minutes or seconds. Just wait for this. All right, calculations are complete. Now we can move on to looking at our data. So we can take a look at our results right here. So we can take a look at graphics, contours, because the project has us find contours and vectors of velocity. So I can just name this velocity underscore contour. Velocity, velocity magnitude. Don't need to select anything. Just save and display. We can see that, yep, flow near the surface is slower than just the flow above the boundary wall. So we save this, save and display. So we can close that out. Then we can go into vectors and create another one. Vectors, velocity underscore vector. We can change vectors, this to save and display. Here they are. They look all good. So we can hit save and display again and then close. And then we can go to scene, velocity contour, velocity vector. We can change this to about 40% transparent. It sounds good. Save. We can name this scene just like velocity underscore scene. And save and display. And this will give us what we need for part A. It is a nice vector field and contour map of our flow. So we can zoom in at the boundary. It's all good. So the next part of part A, I believe, was finding the pressure contours. So we can go back to contours. You can name this pressure or whatever if you wanted to save it. So then we can just hit save display for static pressure. Zoom out. Here's our static pressure. We could save that, take a screenshot. Dynamic pressure, save and display right here. And then we could also get total pressure, save and display. all right there. And then we can move on to the next part of the project, which, let me pull up my instructions real quick. Yes, it was finding the velocity, uh, uh, let me look at it. The velocity profile at points x is equal to 25, x is equal to 50, and x is equal to 75. So to do this, we're going to have to start with making some new surfaces, line rakes. So we can name this first one x.25 for 25 centimeters. So our x will be constant, 0.25, 0.25, and then our y will go from 0 to 0.1, which is our height. And so then we can just create, and then we can move on to the next one. So x.50, which will be our 50 centimeter line. So move this to 50 and 50. 0.1 is still okay, so we can create. And we can move to the last one, x.75. Change that to 75 and this to 75. Create and close. So now we have our 3 lines. They should be here. And then we can move on to plotting these on an XY plot. So we can move our position on the X to position on the Y. You can order the points. That usually works a lot better in Excel. And you can change, and you can select all these. And we're going to be using direction vector. And instead of pressure, we'll have I believe it was mesh. We actually don't need to select position on the y-axis. We can change this to the y coordinate and then change pressure to velocity and velocity magnitude. And this should give us our plot. Yep. We can see our 3 nice little lines. This gap only appears when you select order points. So if you wanted a nice clean line for a picture, just write it, the gap's gone. But using ordered points is very good for the Excel work that we're going to do later. So do this, and then we can get right to file, and then you can click right to file, and then save that wherever you want. And then you can go into your Excel, and then create something like this. You can make a little table or graph, and then use your boundary layer thickness equation and your velocity to find your boundary layer thickness, all right here. So going back into here, we can start on our next step. That should have been all for part B. So now we can move on to part C, which is plotting the wall shear stress and skin friction coefficient. Both of these are fairly simple. So we can start by going out of this, back into it, and then changing this to wall fluxes, wall shear stress. Then you're using the x-axis direction vector. And then you're going to be using plate. And then you could save plot, and that'll be your plot for wall shear stress. And then you can also do the same for skin friction coefficient. Save the plot, and then for both of these equations, you can just write to file, so you can use your processing to work to find your theoretical values for these, which we can do in Excel, which looks something like this and this. That'll be all for part C. Now we can go on to part D, which is getting the drag coefficient. This one's a little bit more complicated than everything else, but shouldn't be a problem. So we can close our solution y plot, And then let me take a look at my instructions once again. So I'll need to go to sorry, I'm just getting my instructions. So reference values. These were under boundary conditions. Here they are. We need to change these to fit our model. So 1.2 density and changing our viscosity over to the 1.8 specified in the project guidelines. And then we can move on to finding the drag coefficient. This is which would be in the report section. Report definitions. We're going to create new, and it would be force report on drag, and then so we can get drag coefficient on plate, and then we can hit OK. Oh, oops. I actually wanted to hit compute. Actually, something was wrong. I forgot. I needed to put in velocity of 2 in this. So we hit compute again. And this right here, this CD of 0.0041693986 would be our drag coefficient, which would be right here. You can copy that in, and then you could calculate it using the theory, which would be like right here. And you get something like this. And that should be all for my part 1 of project 3, flow over a flat plate. So that'll conclude this video. Thank you for watching and grading, and have a good day.